Hello. I'm Partha Thirumalai. My main interests are in compiler optimization, CPU architectures, and of course, performance analysis and tuning. So today, following on to Dennis's talk, I'm going to be presenting some results on this chip. So we won't do a lot of the architecture stuff, which has already been covered. We'll just dive straight into the performance part of this presentation. Actually, this talk is going to be a two-part sort of presentation. The second part will be done by my colleague, Ruud van der Paas. In this first part, I will cover basically the performance of the UltraSPARC T2 processor on industry standard benchmarks. So you get a feel for what industry standard benchmarks are and how this T2 is faring on those kinds of workloads. So before we get started, let's do a little recap, because Dennis presented a lot of features on the UltraSPARC T2 processor. And in this particular part of the talk, what we're going to be focusing on are floating point intensive sort of HPC kind of workloads. And if you go back and look at what Sun did several years ago when we first introduced our aggressive CMT offering, the UltraSPARC T1, that chip had support only for incidental floating points. So it really wasn't designed for heavy-duty floating point applications. It had 32 threads, 8 cores, and all that, but all of those threads shared one floating point unit. What we have done now in the UltraSPARC T2 is we have added substantial floating point capability. So effectively, we have now one floating point unit per core. So you have 8 cores, and each of those cores have one floating point unit. Also, in the previous chip, some of these important instructions like F square root and F square root D, both single and double precision, were not implemented in hardware, so they would trap the software and take quite a long time to run. In addition, there were also some viz instructions. These aren't very common, but if they do occur, they would also trap and get executed in software. So now in the UltraSPARC T2, these kinds of handicaps are gone. And so if you look at the UltraSPARC T2 design, integer and floating point are pretty much on par. So it's supposed to perform well, equally well on both kinds of workloads, integer and floating point. So if you look at basic floating point characteristics, so before we get into applications and stuff, if we just look at the flow and compare the two designs, the T1 and the T2, at the same clock rate, let's say 1.4 gigahertz, then you can see that the theoretical flops, so if you just compute the theoretical flops, that's gone from 1.4 to 11.2. So that's a gain of 8 times, 8x improvement in this new chip. But in fact, the impact is much more. In the previous chip, the achievable peak due to various other restrictions inside the chip was only 0.117 gigaflops. And now, on the UltraSPARC T2, you can actually achieve, the peak achievable on this chip is 11.2, and that's an improvement of about 100x. So that's nothing to ignore. So significant improvement. And then if you also look at the instructions themselves, like the basic instructions like floating point adds and multiplies, the latency has improved by about 5x. And the throughput, the maximum number of flops that you can do, has also gone up by about 100x. And similarly, divides and square roots have also gone up substantially. Divides, you can now do 15 times more in throughput. And square root, which was previously trapping and getting executed in software, has now gone up by about 300x. So very substantial improvements in this chip. So now suppose you want to take this chip and then you want to say, I have this HPC application. What do I need to do to get the most out of this new design? Well, for best results, what you need is you need to use parallelism, because it's a CMT design. It has 64 threads. And the more threads you have, the happier the chip is and the more performance you can get. So this parallelism can actually come in different forms. So at least 2 forms at the highest level can be distinguished. One is the workload level parallelism, where you basically have a job. The job may be serial, single-threaded job, but you have many such jobs to run simultaneously. So this might happen, for example, in our compute ranch. There are many CAD applications that people run, and some of them are floating point intensive. They can actually submit these jobs, and different people's jobs run simultaneously on the box. And the second, of course, is traditional parallelism, where actually the threads come from within one application, so that the application has been parallelized, and you get the threads from that. And in reality, you can have a combination of these two forms too, because you can have an application that's been parallelized and maybe tuned for up to, say, 4 or 8 threads, but as long as you have 4 to 8 of those applications to run simultaneously, you can basically get the full benefit out of this chip. So let's take a look and see how well parallelism and the floating point capability of the UltraSPARC T2 can be exploited. So with regard to industry standard benchmarks, there are many. And today I'm going to basically, in the limited amount of time we have, use the SPEC CPU 2006 floating point benchmark. And I'm sure that not all of you are really familiar with this suite. So let me take a few minutes to explain what this benchmark is so you can understand the results that I'm going to show. So what SPEC did is it actually launched a multi-year effort in trying to get some applications for the suite. So it invited submissions from anyone. And in fact, people were paid for those submissions. You would get paid for a submission even if it wasn't selected to go into the final suite. And after a long and exhaustive search, they actually ended up with 17 applications written in Fortran 90, C, and C++. The total size is about 1.3 million lines of code. If you do a full compliant run on this chip, it would take days. So it's a fairly significant workload. And the idea that SPEC had, the criteria that it used in selecting these applications, was that the applications must be widely used in their areas, and they were implemented using modern algorithms, not something that's outdated. And they also asked for multiple inputs for each of these applications, so it would exercise the application fairly thoroughly. And when you do report results, there are fairly strict rules on how to run this benchmark. You have to have these disclosures and stuff like that. So there are fairly strict rules for how you actually run and report results. They do not allow source changes. So this might be something that is slightly different from real world, because if I'm tuning a program that I own, I might be willing to change the source. But in what SPEC does is, for the SPEC CPU 2006 floating point benchmark, is source changes are not allowed. The focus really is on user code as optimized by a compiler, so that you can use your compiler and it produces optimal code for that architecture, and then you run that. And typically these applications have flat profiles. They exhibit a rich variety of execution behavior. So meaning that there are all kinds of memory accesses, all kinds of branch predictions, mispredictions, all the typical CPU things that we measure. So what are these application areas? I'm not going to go through all of them in detail here, but some of you might be familiar, maybe even using some of these application areas or applications themselves, like B-Waves is a CFD code. It simulates blast waves. Then there's quantum chemistry, quantum chromodynamics, all kinds of different problems. A little bit heavy on CFD. It looks like there are 3 applications that are in the area of CFD, but there's all kinds of other mathematics and computational biology, speech recognition, and a variety of different areas are covered by this suite. So what does the US T2, UltraSPARC T2 do on this benchmark? So actually, this chip has delivered record throughput. So by throughput, what we mean is SPEC provides this throughput metric where they allow you to run multiple copies of this benchmark, and they measure, the metric is the number of jobs completed per unit time. So on a single socket basis, so a single chip number, the UltraSPARC T2 was the highest result when I last looked. So it was even a little bit higher ahead of the 4.7 gigahertz power 6 chip, and that chip was running at more than 3x the clock rate and had more than 3x the peak flops of the UltraSPARC T2. And remember that the UltraSPARC T2 does all of this while giving you the benefits that it typically does with power, space, and cooling. A little bit more detail into the results. Normally, people just quote this one final number, the geometric mean, which is on the right side of this bar graph. And that's the only number that is typically quoted. But if you, in fact, go and look into the detailed disclosures, there are all kinds of numbers inside that report from which this geometric mean is derived. So we can actually summarize the numbers for each of these 17 applications, and you can see how the applications are actually faring. And you can see that there are some applications where the UltraSPARC T2 is a bit behind the IBM chip, but overall it's not so bad. And in the end, the final geometric mean is in fact higher, slightly higher. This is the same data as in the bar chart. Bar charts, I find them very difficult to really spot out the percentage differences. Everything always looks equal on a bar chart to me. And so here, if you see the percentage deltas, you can see that on the geometric mean, it's about 7% better. There are some negative numbers. Those are the applications where it's a little behind. But there are also applications where it's considerably ahead. So the main message here is that there is this chip, even though it is running at 1.4 gigahertz, the CMT design, the fabulous memory bandwidth, and all the improvements made to the floating point side is enabling it to deliver significant performance on something that we wouldn't have thought possible when we first looked at the UltraSPARC T1. So now I'll move on to the second benchmark. This is the SPEC OMP 2001 benchmark. And this benchmark doesn't measure throughput. It actually measures the time to completion for a single application, except that the application has been parallelized. And by using OpenMP, these applications have been parallelized. The one difference between CPU 2006, FP, and this benchmark is that here source changes are allowed. So if a vendor wants, they can go and make some small source changes. However, the rule requires that those source changes be provided, made public, and be provided to others. So if you find a trick, you must share it with everybody else. And so in effect, what happens is people find these small source changes, and then the whole community is using them. So in a sense, it's nicely parallelized collection of suite. Otherwise, the applications are similar to those in the CPU 2006 floating point benchmark. There are two data sets provided, medium and large, and today I'm going to be talking about the medium data set. So once again, on this benchmark, actually recent submission on the UltraSPARC T2 shows that it has delivered a world record kind of single chip result. And it was, in this case, a comparison could be made with a 2-chip quad-core 2 gigahertz Opteron system, where also the numbers are submitted. That machine has substantially more flops, and the UltraSPARC T2 was almost on par with that 2-chip. So a single UltraSPARC T2 chip was producing a number that was nearly as good. So here's the bar graph of these 11 applications. So you can see once again that across the board it's very reasonable. The UltraSPARC T2 versus 2 quad-core Opteron chips is what is shown here. So it's really 1 chip versus 2 chips. And on the last part, that is the final number, is the geometric mean, and the two systems are practically equal. I think the UltraSPARC T2 is like 1% ahead. So this is the same data, and you can see these are the numbers. You can actually go to the spec.org website. There is more detailed information over there. I won't repeat it in the interest of time. And then you can get a good feel for like how these applications are performing. And there are possibilities, that you really need to explore with this box. This box is still very new to us, and I don't think we have actually tuned it to death. The whole design, the architecture, everything, we are learning something, but already it is looking pretty good. So one thing we did find is that initially when we got this CMT design, we thought that optimization is not going to be very critical, but in fact it is fairly important. So we thought the simple pipeline, the fact that as soon as a long latency instruction is issued, the whole thing switches to another thread, all of those things would make things like traditional optimizations less important. It is not entirely true. Things like instruction scheduling may not be critical, but things like cache blocking and tiling are, in fact, quite critical. And so one thing we found is that optimization should definitely not be ignored when testing the UltraSPARC T2. So one experiment we did to gauge this was to use the same kind of binaries on two SPARC machines, the UltraSPARC 4 Plus and the UltraSPARC T2. And this experiment, what it did was we basically turned off all optimization and then turned on fairly aggressive, but not extreme. It's not extreme optimization of every individual thing. And nor did we use any special directives or assertions. We didn't make any source changes. So it's basically what traditional but aggressive optimization can do to your program. And we measured what the delta was on these two machines. On the UltraSPARC 4 Plus, which is a very traditional superscalar CPU, 4 issue, and all those things, the range of gains was 2.4x to 30x on this suite. And the average gain was like 9.4x. But on the UltraSPARC T2, we actually found very good gains also. We found an average gain of 5.2x, and you certainly don't want to throw away a part of that. So maybe you don't try too hard and you just get 4x. But if you go from 4x to 5x, that's a 25% boost. So my point here is that do try to use the same kinds of optimization levels that you're accustomed to with previous machines. Another thing, of course, is parallelization. This is very valuable with UltraSPARC T2 design. And because it has so much threading capability, it has such good bandwidth and so on, we find that AutoPar, which is our acronym for automatic parallelization, this is done entirely by the compiler. All you have to do is to add a flag, and that can be interesting in more cases than you might expect. And it can also be an easy starting point. So you don't want to maybe start with parallelizing a traditional serial application on day one, but you just want to try AutoPar. It may not give you the best result, but it'll get you started. And it can work in conjunction with other things as you proceed. And once again, we try to evaluate the impact of automatic parallelization on traditional versus these new designs. And we found for this suite that 4 of the 14 applications on the UltraSPARC 4 Plus, which is our traditional superscalar design, showed noticeable gains. And on the UltraSPARC T2, 5 of the 14 applications actually showed pretty good gains. I'm sure more of these applications can show gains, but in this particular case, you should remember that what we're trying is just adding a flag. And for that, if I can get 5 cases, gains of between 2 and 8x, that's pretty good. So do give it a shot. And with that, I will stop with this part of the talk. The summary really is floating point is significantly enhanced, and we are seeing very good performance on both workload level parallelism as well as application level parallelism through parallelizing using OpenMP. And of course, don't ignore optimization and parallelization for the UltraSPARC T2. So now we move on to the second part of the talk.